Welcome to GKE IP ranges. Welcome to the channel. Please consider subscribing. I produce videos covering AWS, Azure, and GCP on a daily basis. Please also hit the bell button to get notified. Welcome everyone. Today we are diving into one of the most important yet often overlooked aspects of Google Kubernetes engine, IP range management. Think of this as learning the city planning fundamentals for your Kubernetes clusters. Just like a real city needs proper zoning and enough addresses for all residents, your GKE cluster needs carefully planned IP address spaces. By the end of this presentation, you will understand how to properly plan, manage, and expand IP ranges in GKE, which will save you from those dreaded pod scheduling failed errors down the road. The city planning analogy. Let me start with an analogy that makes this concept crystal clear. When you create a GKE cluster, you are essentially becoming a city planner for a digital metropolis. In traditional networking, we often think about IP addresses as simple technical identifiers. But in Kubernetes, and especially in GKE, IP addresses become a precious resource that need a careful allocation strategy. Think of it this way. If you were planning a new city from scratch, you would not just randomly assign addresses. You would create districts, zones, and reserve blocks for different purposes. In GKE, these zones are defined by CIDR blocks. Those slash notations like /16 or /24 that define how many IP addresses are available. A /16 gives you about 65,000 addresses, while a /24 gives you only 256. The choice affects your cluster's entire scaling capacity. Just like any real city, you need to zone different areas for different purposes. You need residential areas for your applications, commercial districts for services, and infrastructure zones for the underlying systems. The key difference is that in digital city planning, we can be much more precise about boundaries and even expand certain zones later. This planning phase is crucial because poor IP range design can lead to expansion problems later. Unlike physical cities where you can sometimes annex neighboring land, in Kubernetes networking, some ranges are permanently fixed once the cluster is created. The 3 essential IP zones. Now let's dive deep into the 3 critical IP ranges you need to define for any VPC native GKE cluster. Understanding these ranges is fundamental because each serves a completely different purpose in your cluster's networking architecture. First, the node range. This is your infrastructure zone. This range is called the primary range because it's directly associated with your VPC subnet. Every worker machine, or node, that joins your cluster gets an IP from this range. When you run kube control get nodes, those IP addresses you see come from this range. This is critical infrastructure. These IPs need to be routable within your VPC and potentially from on-premises networks if you have hybrid connectivity. Size this conservatively but adequately. You can't expand it later. Second, the pod range. This is your massive residential district, and here's where it gets interesting. This is a secondary range, meaning it's overlaid on your VPC subnet but operates independently. Every application instance, or pod, gets its own IP from here. When you run kube control get pods, those IP addresses come from this range. This needs to be your largest range because in a busy cluster, you might run thousands of pods simultaneously. The beautiful thing is that GKE handles all the routing complexity. Pods can communicate directly using these IPs even though they're in a secondary range. Third, the service range. This is your commercial district with stable PO boxes. This is also a secondary range. Services provide unchanging addresses that route traffic to your pods, even as individual pods come and go. When you create a service and run kube control get SVC, those cluster IP addresses come from this range. These IPs are only routable within the cluster. They're virtual endpoints that kube proxy manages through IP tables or IPVS rules. Notice how each zone serves a distinct purpose and has different scaling requirements. Node IPs need external routability, Pod IPs need high volume but internal-only routing, and service IPs need stability but lower volume. Understanding the architecture. Let me show you exactly how these ranges work together in the actual GKE architecture, because understanding this relationship is crucial for troubleshooting and planning. Your VPC subnet is like the city limits. It defines the overall boundaries and is created with a primary CIDR block. For example, if you create a subnet with 10.100.0.0/16, that defines your city limits with about 65,000 potential addresses. Within those boundaries, you pre-allocate specific ranges for different purposes using secondary ranges. Here's the key insight. These secondary ranges are logically separate but physically overlay the same subnet infrastructure. When you define a secondary range like 10.110.0.0/16 for pods, Google Cloud sets up additional routing rules so that traffic to those IPs gets routed correctly to your cluster nodes, where the kubelet and CNI plugin handle the final delivery to the correct pod. The relationship works like this. Your GKE cluster is deployed into the subnet and claims these pre-defined ranges for its use. The cluster master, which you don't manage, knows about all three ranges and coordinates IP allocation. When a new node joins, it gets an IP from the node range. When a pod is scheduled to that node, the kubelet requests an IP from the pod range. When you create a service, the API server allocates an IP from the service range. This is why proper planning is so important. You're essentially doing the zoning before you build anything. The cluster can only use what you've pre-allocated. Changes later require careful expansion procedures that I'll show you, but some ranges like services and nodes are permanently fixed. One more critical detail. The secondary ranges don't consume space from your primary range. They're additional address space overlaid on the same subnet. This is how Google Cloud can provide massive IP space for pods without requiring equally massive VPC subnets. The dreaded IP exhaustion problem. Now let's talk about what happens when your city planning falls short, specifically, pod IP exhaustion. This is one of the most common operational issues I see with GKE clusters, and it often catches teams by surprise because their applications are running fine until suddenly they can't scale anymore. Here's exactly what happens. Let's say you initially allocated a /20 subnet for your pods, thinking that's 4096 IP addresses. Surely that's enough. But as your application grows successful, you need to scale up. When Kubernetes tries to create new pods, they get stuck in pending status. If you run kubectl get pods, you'll see them just sitting there, never becoming ready. The real clue comes when you run kubectl describe pod and look at the events section. You'll see an error message like 0/3 nodes are available, insufficient free pods, or more specifically too many pods on node combined with no available IP addresses. What's happening under the hood is fascinating and important to understand. Each GKE node has a finite number of pod IP addresses pre-allocated to it from your pod range. For example, on a standard E2 medium node, GKE might allocate a /24 subnet, 256 IPs, to that node. When that node runs out of its allocated IPs, it cannot schedule new pods, even if the node has plenty of CPU and memory available. This is exactly like a city running out of residential zoned land. You want to build more houses, but there are no available addresses to assign to them. The infrastructure nodes is there, the demand new pods is there, but the addressing scheme has become the bottleneck. The good news is that unlike many other Kubernetes networking issues, this one has a clear solution that doesn't require recreating your cluster. You can expand pod ranges dynamically, which I'll show you step by step. The expansion solution overview. Here is the beautiful thing about GKE's VPC native networking. You can dynamically add additional pod ranges to a running cluster. It's like your city acquiring adjacent land and zoning it for new residential development, but with much less paperwork. However, there is one critical limitation I need to emphasize up front, and this is where many people get tripped up in their planning. You can only expand pod ranges. You absolutely cannot expand node ranges or service ranges on a running cluster. This is a hard architectural limitation. Why this limitation exists is important to understand. Node ranges are tied to your VPC subnet's primary CIDR and to Google Cloud's routing infrastructure. Changing them would require rebuilding fundamental networking components. Service ranges are embedded in the cluster's kube proxy configuration, and changing them would break existing service discovery. Pod ranges, however, are more flexible because they are managed by the CNI plugin, Container Network Interface, running on each node. The CNI can be reconfigured to allocate from additional ranges without disrupting existing pod-to-pod communication. The expansion process involves 3 main steps, and each step serves a specific purpose in the overall networking architecture. First, you add the new IP range to your VPC subnet. This tells Google Cloud's network infrastructure that these IPs are valid and should be routed to your subnet. Second, you tell your GKE cluster about this new range. This updates the cluster's IP allocation policy so it knows about the additional address space. Third, and this is the step people often miss, you create a new node pool that actually uses the new range. That third step is crucial because existing node pools are wired to specific IP ranges and cannot be changed. Only newly created node pools can be configured to use additional ranges. This design ensures that existing workloads continue running without any networking disruption during the expansion process. Step 1. Expanding your VPC subnet. Let's walk through the actual commands with detailed explanations of what each parameter does and why it's necessary. The first step is adding a new secondary IP range to your existing VPC subnet. The gcloud command you see here is gcloud compute network subnets update. Let me break down each component. The compute network subnets part tells the gcloud CLI that we're working with VPC networking, specifically subnet configuration. The update verb is crucial. We're modifying an existing subnet, not creating a new one. The region parameter specifies which Google Cloud region your subnet exists in. This must match exactly where your existing subnet was created. If you're not sure, you can check with gcloud compute network subnets list to see all your subnets and their regions. Now here's the key parameter. Add secondary ranges extra-pod-range-110.200.0.0/16. This is doing several important things. The add-secondary-ranges flag tells Google Cloud to add a new secondary CIDR range to the existing subnet. The format is name equals CIDR block. The name extra-pod-range-1 is arbitrary but should be descriptive. You'll reference this exact name in subsequent steps. The CIDR block 10.200.0.0/16 is carefully chosen. It's a /16 which gives us about 65,000 IP addresses, plenty for pod expansion. Critically, this range must not overlap with any existing ranges in your VPC or any peered networks. I chose 10.200.x.x because it's in the private IP space and clearly different from typical ranges like 10.0.x.x, 10.100.x.x, or 192.168.x.x. When this command completes successfully, Google Cloud has updated its routing tables to recognize that traffic destined for 10.200.0.0/16 should be routed to your subnet. However, your GKE cluster doesn't know about this new range yet. That's step 2. This step just creates the zoning at the Google Cloud networking level. It's like the City Council officially designating a new area as available for residential development, but the Housing Authority, your GKE cluster, doesn't know about it yet. Step 2. Informing your cluster. Now we tell the GKE cluster that it's officially allowed to use this new IP range. This step is crucial because it updates the cluster's internal IP allocation policy. The command gcloud container clusters update is specifically for modifying running GKE clusters. Let me explain each parameter in detail. The cluster name your GKE cluster must match exactly. You can check your cluster names with G Cloud Container Clusters list. The zone US Central 1A must match where your cluster is running. For regional clusters, you'd use region US Central 1 instead. The critical parameter is additional pod ranges extra pod range 1. Notice that this is the exact same name we used in step 1. This creates the connection between your VPC subnet's new secondary range and your GKE cluster's understanding of available IP space. What happens internally when this command runs is quite sophisticated. The GKE master updates its IP allocation policy to include the new range. This policy is stored in the cluster's configuration and is used by several components. The cluster autoscaler, to understand IP capacity when adding nodes. The kubelet, to know which ranges it can request IPs from. And the CNI plugin, to actually assign IPs to pods. However, here's the crucial point that trips up many people. Your existing node pools are still wired to use the original pod range. This is by design to prevent any disruption to running workloads. The existing allocation doesn't change. We're just expanding the available options for future node pools. You can verify this step worked by running G Cloud Container Clusters. Describe your cluster name zone your zone and looking for the additional pod ranges config section in the output. You should see your new range listed there. Think of this step as updating the city planning department's records to show the new residential zone. The zoning exists, the planning department knows about it, but no construction crews are assigned to work there yet. That's step 3. The critical third step. Here is the step that many people miss, and it is absolutely essential. You must create a new node pool and explicitly configure it to use the new IP range. This is like opening the new subdivision for construction and assigning specific construction crews to work there. Let me break down this G Cloud Container Node Pools Create command in detail because every parameter matters. The node pools create tells us we are creating a brand new node pool. The name new apps pool is arbitrary but should be descriptive. This helps you identify which node pool is using which IP ranges later. The cluster equals your GKE cluster and zone equals US Central 1. Parameters must match your existing cluster exactly. The num nodes equals 1 is just the initial size. You can scale this up later or enable autoscaling. But here is the absolutely critical parameter. Pod range equals extra pod range 1. This tells the new node pool which IP range to use for pods that get scheduled on its nodes. Notice this is the same name we used in steps 1 and 2. This creates the complete chain. VPC subnet, cluster policy, node pool configuration. What happens when this node pool comes online is quite elegant. Each node in this pool gets configured with a CNI configuration that allocates pod IPs from the 10.200.0.0/16 range instead of your original pod range. When pods are scheduled to these nodes, they get IPs like 10.200.0.5, 10.200.0.6, etc. Your existing node pools continue operating exactly as before, using the original pod range. This design ensures zero disruption to running workloads while providing you with the additional IP capacity you need. Now, when you deploy new applications, you have choices. You can let the scheduler place them anywhere. They might end up on original nodes with original IPs, or new nodes with new IPs. Or you can use node selectors or affinity rules to specifically target the new node pool if you want to ensure they use the new IP range. This step essentially opens your new residential subdivision for business. Construction crews, the kubelet and CNI, are now assigned to work in the new area and will build houses, pods, with addresses from the new range. Understanding the expanded architecture. Let me show you what your cluster architecture looks like after the expansion, because understanding this helps with both troubleshooting and future planning. The diagram illustrates how you now have two distinct node pools drawing from different IP ranges, but operating within the same cluster seamlessly. Your original node pool, typically called default pool unless you renamed it, continues operating exactly as before. Every pod scheduled to nodes in this pool gets IP addresses from your original pod range. Let's say 10.110.0.0/16. Meanwhile, your new node pool new apps pool is configured to use the expanded range 10.200.0.0/16. When pods get scheduled to nodes in this pool, they receive completely different IP addresses, but here's the beautiful part. They can still communicate with pods in the original pool seamlessly. This works because GKE's VPC native networking handles all the routing complexity for you. Google Cloud's network infrastructure knows that both IP ranges belong to your cluster and routes traffic between them appropriately. From a POD's perspective, it doesn't matter if it's talking to 10.110.0.50 or 10.200.0.75. The network just works. This design gives you tremendous flexibility in how you manage the transition. You can gradually migrate workloads to the new node pool by updating your deployments to use node selectors that target the new pool. Or you can use it specifically for new applications that need the additional IP space while leaving existing applications untouched. One important operational consideration. When you're debugging networking issues, you'll now need to consider which node pool a pod is running on to understand which IP range it's using. Commands like kubectl get pods wide become more important because they show you both the pod IP and which node it's running on. The key insight is that this expansion doesn't disrupt existing workloads while providing you with the additional capacity you need. It's a true hot expansion. No downtime, no service interruption, just additional capacity when you need it. Verification and monitoring. It's absolutely crucial to verify that your configuration worked correctly, and I'm going to show you exactly what to look for in the output because the details matter for troubleshooting. The G-Cloud Container Clusters Describe command gives you the complete cluster configuration in YAML format. This is your definitive source of truth for how your cluster is configured. The zone parameter must match your cluster's location exactly. In the output, you need to find the IP allocation policy section. This section contains all the IP range configuration for your cluster. Let me walk through what each field means. Cluster secondary range name shows your original pod range name. This is usually something like GKE cluster name pods random suffix if GKE created it automatically, or a custom name if you specified one during cluster creation. Services secondary range name shows your service range name, typically GKE cluster name services random suffix. These two ranges are the original ones that cannot be expanded. The critical section is additional pod ranges config with a pod range names array. This is where you should see extra pod range 1 listed. If this section is missing or empty, it means step 2 didn't complete successfully and your cluster doesn't know about the additional range. You can also verify at the node pool level by running G-Cloud Container Node Pools Describe New Apps Pool Cluster Your Cluster Zone Your Zone. Look for the pod range field in the node pool configuration. It should show extra pod range 1. For operational verification, create a test pod in the new node pool and check its IP. kubectl run test pod image nginx overrides spec node selector cloud.google.com/gke node pool new apps pool and kubectl get pod test pod wide. The POD's IP should be in your new range 10.200.x.x. I also strongly recommend setting up monitoring for IP utilization. You can query GKE metrics in cloud monitoring to track how many IPs are allocated versus available in each range. This helps you plan for future expansions before hitting the next exhaustion point. This verification step is your insurance policy. It confirms that all 3 steps completed successfully and your cluster is ready to use the expanded IP space effectively. Best practices and wrap up. Let me leave you with comprehensive best practices that I've learned from managing hundreds of GKE clusters in production environments. First, always plan your initial IP ranges generously, especially for pods. A common mistake is thinking we'll only run 50 pods and allocating a /24 which is 256 IPs. But remember, pods are ephemeral. During deployments, you temporarily have both old and new pods running. During scaling events, you might have many more pods than your steady state. I recommend starting with at least a /20, which is 4096 IPs, for pod ranges, even for small clusters. Second, monitor your IP utilization proactively using cloud monitoring. Set up alerts when you reach 70% utilization in any range. This gives you time to plan and execute expansions during maintenance windows rather than during outages. The metric you want is kubernetes.io/container/network/received bytes count, segmented by IP range. Third, remember that only pod ranges can be expanded. Node and service ranges are fixed forever. For node ranges, consider future cluster growth, including autoscaling scenarios. For service ranges, remember that every service gets an IP, including internal services created by operators and add-ons. A /24, which is 256 IPs, is usually sufficient for services unless you have hundreds of microservices. Fourth, document your IP range assignments and expansion history for your team. Create a simple spreadsheet or wiki page showing cluster name, original ranges with their purposes, any additional ranges added and when, and the total capacity of each range. This documentation becomes invaluable when troubleshooting or planning further expansions. Fifth, test your expansion procedure in a development environment first. While these commands are generally safe, practicing the process reduces stress and chance of errors when you're under pressure to resolve a production IP exhaustion issue. Finally, consider IP range planning as part of your broader network architecture. If you're using VPCs peering, firewall rules, or hybrid connectivity with on-premises networks, make sure your new IP ranges don't conflict with existing networks and that your security policies accommodate the new ranges. With proper IP range management, you'll avoid those frustrating pod scheduling failures and keep your GKE clusters running smoothly as they scale. Remember, good IP planning is like good city planning. A little extra investment up front saves massive headaches later. Thank you for joining me today. Please hit the subscribe button if you haven't done so already. Thank you for your attendance.